Hello, space nerds. How are you doing? Welcome to my talk on what developers can learn from astronauts. You made the right choice coming here after lunch. We're all tired. You don't want to listen to technical details. You want to have cool stories about space, which is awesome. I'd like to start by saying I'm not an astronaut. I have no connection with space. I'm a Java developer with a history in finance, normally. I just like space because I'm a nerd, and so I've read lots of books in the preludes coming up with this and discovered there's lots of great analogies. And I think it's really important that we try and learn from other industries because there's an awful lot to learn that I think there's an implicit assumption we already know everything that we can do. And that's not the case, and so I'd like to give an example of that from not computing science. So this is a guy called Tal Goldsworthy, and he's an engineer, and he was diagnosed with a condition called Marfan syndrome, which is where your aorta, when it pumps blood, is meant to spring back into position. And with Marfan's, that doesn't happen, so it's quite dangerous. And the traditional cure for this is to lob out that piece of your heart, replace it with a metal bit, and then you're on a lifetime of drugs to deal with that. It's a horrible condition. But Tal's an engineer, and when the doctors explained this to him, they said, well, when I've got like a hose in the garden and the pressure drops on that, you just get a bit of duct tape and wrap it round. Can we not just do that with my heart? And so spent 6 months working with engineers then, trying to come up with this piece of duct tape, which was, a medical material, 3D printed to fit his aorta and keep it tight. And he was the first person to undergo this treatment, and it worked. So he doesn't have a lifetime of drugs to do, and he's perfectly well and fine. And this has gone on to be used by lots of other people with this condition. This was a horrible condition that thousands of people every year would have, and they don't need to go through this horrible thing anymore because an engineer got that disease. And that's crazy for me, and I think that's something, there's a lot that every industry can learn from other industries, because generally we don't have much crossover, which is what gave me this idea for doing this talk, because there's lots of stuff that we can learn from space and from NASA, and there's lots of cool stories, basically, which we'll go through today. The main thing that you will take from today, though, among all of the stuff, is that you will make mistakes. People are dumb. And NASA, for me, they are they're incredibly well-funded, they've got the smartest people in the entire world, and they do some really, really silly things. I don't know about you, but as a developer, when if something goes into production and there's a bug or a misrequirement, I go, if I'd done something better, this is a computer science thing. As developers, we're not good at this stuff. And it's not true. Everyone sucks at this stuff. The NASA guys do as well. And my favorite one of these stories is the Mars Climate Orbiter. This wonderful little device. They spent 3 years building it. Cost about $300 million, which is pretty cheap for NASA. And then 286 days to get to Mars, where it's going to go into orbit and come back with lots of sciencey stuff. Except it got to Mars, and then it disappeared. It died. And so NASA's like, what's happened? It's gone crazy. And it turns out that when they did the spec, they had a nice big spec document, like in the good old waterfall days, which they handed to Lockheed Martin. It said, you must use metric units, because English units rule. But Lockheed Martin, being American, were like, we're going to use American units. And for thrust, that's about a 1-to-4 ratio out. So it got to Mars, and then it just died. It just went straight into the atmosphere and burned up. That's insane. That's $300 million down the drain because someone didn't read a spec document. These guys are meant to be smart. And it's also got a very big lesson for us as software guys, which is don't assume people do the right thing. If you're going to someone and saying, I need you to give me an API or a service, write some software that automatically tests it. How NASA didn't have a test harness around this, I don't know. It baffles me. But anyway, people do dumb things. It's not just a software development thing, and that's okay. So that's one of the main lessons you'll get today. But I've got kind of 3 separate little stories which I'm going to go through to hopefully keep you entertained for the afternoon. First one is about building simple systems, which is kind of crazy when you think about space travel. Space travel's hard. There was, in the Gemini missions, that's when we were first proving we could get someone out of Earth into space. The whole thing had about 1.4 million different parts in it. It's a lot of different pieces. When you upgrade that to Apollo 8, which is when we're actually going to the moon, that's gone to 5.6 million different parts. It's a lot of parts. And there was a comedian at the time who liked to joke that every single one of those parts was made by the lowest bidder, which is petrifying if you're strapping yourself to what is effectively a bomb. If you look at the command module, so that's the bit that when they get to the moon that stays in orbit, that's the command module panel. 24 different instruments, 566 switches, and 71 lights, all to be operated by 2 people, or 1 person when the rest of the guys are down on the moon. That's complicated. Can you imagine learning to operate that thing? It's really, really confusing and difficult. When you upgrade that to the space shuttle, that has 1,000 different hardware and software switches and different bits and bobs. So it's incredibly complicated. Or specifically, NASA likes to make stuff complicated. Because you see, NASA has this great history of it's come from the Air Force. The first astronauts were all Air Force guys, pilots, love the checklist, love going gung-ho and manually driving stuff. And that's a very, very NASA thing. And obviously, dumb things happen because of that. So one of my favorite parts of this, because they have to have the documents for this, for how to do all the switches and what goes wrong, it took an extra 5,000 pounds of fuel. That's 2.5 tons of fuel just to send documentation up in the Apollo missions. That's incredible. And these people have to read this stuff. And it obviously leads to problems. So in Apollo 10, which was before Apollo 11 where we landed on the moon, they did everything except the landing bit. And they got the lunar module to really low like they were meant to. And then it spun massively out of control, like 8 times over. NASA said if it had gone a 9th time, they would have died. They were 1 second away from dying. And afterwards, NASA had a big powwow, because they're very good at these powwows, figuring out what they did wrong, because they do stuff wrong a lot. And they came up with, and I quote from the report, a checklist error in switch settings. They'd been doing these switches as they were going down, and they got them wrong, which isn't surprising, because it's incredibly complicated. The same thing happened in the Apollo-Soyuz missions. The crew gassed themselves with toxic, nitrous gas, because they didn't hear each other when they were calling these multiple commands out, and they missed 2, which flooded the thing. Manual processes don't work. I'm preaching to the converted here. It's 2016, we have Agile, we have DevOps. They don't work. They will result in mistakes, which we'd like to avoid. Now, it's not all doom and gloom, because we have Russia. Russia loves automation. Whereas NASA has this background as, gung-ho Air Force pilot, Russia's more background in science. And they build things automated. It's ingrained in their mindset. If they're building something, they will automate it first. They will not look to do it manually at any point. With the space shuttle, after it arrived in orbit, they then have to spend an hour going through checklists and procedures, converting it from flying up mode to orbit mode. In the Soyuz, there is a 1-page checklist to get you from Earth up to orbit. 1 page. I've got documentation for my systems for how to log in that are longer than a page. It's really impressive, and they don't even need that because the whole thing can be completely automated, and they have done it with no one in it, where they can fly the whole thing up from Earth to the space station without any interference whatsoever. So it's a pretty cushy job if you're in the Soyuz, except that's the space of the front of a Beetle. You know the car, the Beetle? That is 3 of them in full space gear in that tiny space. So it's a bit cramped, but at least they don't have to do very much work. And this automation concept also applied to the International Space Station. The US liked to fly its modules up in the shuttle and then use the Canadarm to lock it in and have someone go out and do it. Russia, whack the module on a rocket, fly it up, and it docks itself to the space station. It's a very, very different mindset. So my message to you about this, be Russia. It's important for developers that we embody that sort of mindset, because the thing is, everyone here knows automation is good. But I think everyone here probably also still has the approach where you build something, you'll manually deploy it, you'll manually create your environments, and then later on you'll come back and you'll go, all right, let's automate this stuff now. Automation is good, we need to do this, we're causing problems. Don't do that. Automate from the very, very beginning. Because manual processes, as we discussed, they have a lot of risk, but they're also a silly thing to do. You guys, you're developers, you get paid a ton of cash because you're really smart so that you can build systems, not so that you can then type scripts and run scripts. That's a bad use of your time. We shouldn't be doing that. And every time you do that, every time you run a script over some logs to generate a report, every time you manually do it, you're reinforcing that that is the correct thing to do. And it isn't. So when you leave today, if you're building any new system, when you've got Hello World working on your box, automatically deploy that to your environment. I don't care if it's with a script, if it's with Puppet, if it's with Ansible, if it's with a build chain. Just get something, because it's a lot easier for you to improve your automation if there's something there, because you're building with your mindset of automation is the right thing to do, not of let's tack it on afterwards. And okay, so not everyone's building new systems. Well, let me just have a quick check. When you check your code into Trunk at the moment, who here has that code automatically deployed to an environment? More than I expected, but still less than half of you. Start there, because once you've got one environment working, it's much easier to upgrade the rest of them. And then you never have to think about it. That's the best part, is once it's done, you never have to think about this stuff. Because you'll do this for your code, and you should do this for your environments as well. We have Docker. We have virtualization. There is no reason why now, on an evening after you've left work, your environment should be deleted, they should be recreated and automatically deployed. And you will never have a Snowflake server again. And you'll never have to think about it, leaving you to come in the next day, put your headphones on, and code all day, which is what we love doing. So, be Russia. They were also ahead of us in terms of the Agile game, and I use Agile in the loose space-based equivalent. So if you look at the shuttle again, so they first conceived of the space shuttle in 1969. That's when they said, yeah, let's go ahead and build it. And it took 12 years of and then it was live for 30 years. It's 135 flights. That is an awful long time for when you've effectively built a monolith. This couldn't be changed. The final flight was the same as the first flight, with the exception of some modifications they made for safety due to the shuttle disasters. To give you some context, when the first shuttle flight happened, I had a mobile phone I could we now have an iPhone 4. The iPhone 4 would destroy the computing power inside a shuttle. This is the shuttle, right? So they had 4 of these beastie custom computers. Which fortunately they never had to use, because I don't understand why they thought one backup computer would be better than any of the 4. Just choose a side. In 1990, they got a huge upgrade on these systems where they upgraded the memory to 1 meg. 1 meg, that's to power a space shuttle. It's insane. But this, I'm hoping, is obviously coming to you. You can see there are some parallels with waterfall development. The wonder that is. They spent 12 years of requirement. Before. If you then flip that over to Russia and the Soyuz, so the Soyuz space station, it was the Soyuz in 1961 as well, at the very start of the space race. It's the same aircraft, but the difference is it's been built in an iterative fashion. There's been 6 major iterations between then and now, but every single flight comes back and they have interviews with the astronauts, they have telemetry data, and then they make changes. Every single one is completely different, and they improve it, and that's led to it being the most stable and reliable launch system that has ever existed. It's a great piece of kit, like not very comfortable, but it does the job, and they're constantly improving, and it's got 1,000 flights under its belt, and it looks like it's going to hit 70 years before they come up with a replacement for it. It's good. Iterative development works. Sorry for the terrible graphic on that, but you have to get what you can off Wikipedia. Fixed. But in comparison to IT, we know about this already. Building monoliths is bad, particularly with our drive now towards microservices as well. The Soyuz is effectively a microservice. So if you take someone like Sam Newman, he says that microservices should be rewritable in about 2 weeks. The Soyuz is kind of the equivalent of that. Every time the Soyuz comes down, they then rewrite it. They have the basis of it there because they've done it once, but they then improve it and improve it and improve it. The first Soyuz that flew up would not do the job that it does now of the ferry to the International Space Station. But they got there through increments. They've had 1, 2, and 3-seater configs. They've had big and small solar panels. They keep changing it, and it's got to the job where it needs today. And if they needed to do something else, they needed to get it to the moon, they could probably do it because they can keep improving it incrementally and throwing it away. So build systems that can improve in small steps. There's nothing that annoys me more than over-optimization and eager optimization, where you try and solve all the problems of the world up front in your software. You cannot know what's going to happen. It's much better to build a small solution and then improve it and improve it. And if you start off with clean code, that's dead easy to do. But it's really hard to do clean code if you're eagerly optimizing. If you're starting off by going, right, I've made this amazing algorithm to make this go really, really quickly, don't do that. Make a rubbish algorithm that's dead easy to understand, and then if it's not fast enough, and I bet 90% of the time it'll be fast enough, but if it's not, then by all means improve, because you've got this beautiful clean code around it. Build systems that you can improve in little steps. That's the main thing I want you to take away from that. So that's the first of the stories. The second is kind of advancing what we discussed before. Even the smartest people make mistakes, which is true. And it's something that I took to heart doing the research for this, because I often get imposter syndrome as a developer. And it's kind of like, OK, it's nice. It's not just us. So I'd like to start by talking about the Mars Rovers. Now, this is a great picture. I love this picture. Drawn by the Mars Rovers on Mars. It is authentic. The best part about this, though, is that it takes 20 minutes to get a signal to Mars. And it's a small bandwidth, so it takes ages to do the signal. So what they do is they do all the instructions on Earth in a test bed the day before to make sure it doesn't overheat, won't damage any components. Then they have a meeting with all the business people to sign off that it's OK to do it. And then they send the signal. This took 2 days of UAT and business approval to do. It was not a mistake, whatever NASA say. Either way, that was by the Spirit rover. What I want to talk about is Curiosity, which is this giant, big, hulking beast on the right. It's like a tank. Like in The Martian 2, Matt Damon's going to be riding it across Mars like a horse. And it's huge, and it caused a lot of problems when they were trying to figure out how to land it, because Mars has got this terrible atmosphere. In the Moon, there's no atmosphere. So you don't need a heat shield. You just kind of like slow yourself down near to the surface with rockets. Earth, great hulking big atmosphere. So you have a big heat shield, which slows you down. So if you're the space shuttle, you can just glide down to Earth. Mars is annoying because it has enough atmosphere that you need a heat shield, but not that it'll slow you down, so you still need rockets. And that's all really heavy and complicated. So the solution they came up with, the 2 rovers on the left, was, I'm going to do that, airbags. They literally just threw the thing at the floor and let it bounce around, which is a problem because they're really susceptible to getting ripped. It means you have a landing area the size of a small country, which is really hard to do if you're trying to choose scientific areas, because the area has to have no big rocks, and it's really hard. And for Curiosity, they weren't able to do it because the airbags would have been ginormous because you have a tank that you're trying to land. So they had to come up with a better scenario. And that's when they came up with this wonderful thing, the sky crane. When they first proposed this at NASA, it was laughed out the room because it's so complicated. You have like parachutes to slow you down, and then you have this cool thing that like does a booster, and then it drops it, and it's like something out of sci-fi. And you can't test this stuff on Earth because we have different atmosphere, we've got different gravity, and so it got laughed out. By the way, they concluded they had to go with it. And so, OK, we're going to build this cool sky crane. How on Earth do we do it if we can't test it on Earth? And the answer is computer models. Go computers. And so they spent ages building these brilliant, brilliant models which took into account, the weather patterns, the areas it could be landing in, just everything to try and make sure that it works. If it didn't work, this thing cost $2 billion to make, $2.5 billion to make, and about 8 years of work. That would be really sad if they messed it up. And if it went in too fast, they'd crash the rover into the ground. If it went in too slow, they'd drop the rover from a height and it would crash. Or if they took too long about it, because weight was such a key, they'd run out of fuel in the sky crane, it would crash on top. And that almost happened. The sky crane almost did crash on it. Like, fortunately, it went OK. The Curiosity rover's there, and it's taking selfies and doing good science. But NASA, as I said, they went back and they did a powwow, and they went, OK, what have we got wrong? How come we messed this up? And they missed one crucial variable. Gravity. I think I would have got that one, but... And this is when I keep going on about, smart people do silly things. NASA do amazing things as well, but there are some mess-ups which reaffirm my, humanity. And gravity, they missed it out. So they had it in, but as a constant. And it turns out gravity isn't a constant. It's a variable. It varies depending on, the density of the areas and the hills that are around it. And so it almost ran out of fuel because the gravity was stronger in that area. It's a big mess-up. But that wasn't the only problem. So you've all had a system where you've had a bug, and you fix that bug in production, and then about 6 months later, it comes up again because someone's re-implemented the same bug, and you go, come on, we've done this, and your business gets really pissed off because they've had it. And you're like, oh, if only we're better at knowledge transfer, if only, our team spoke to each other. This wasn't the first time that NASA had done it either, because when we first went to the moon, we discovered they're called mascons, these area of high gravity. And it messed up some of the things on the moon as well, and they figured it out and they got around it. We even have mascons on Earth. Hawaii is one. They knew that this was a problem, but because the Apollo team and the Mars team were different and no one had bumped into each other and had a coffee and said, oh, have you thought about this? They almost crashed $2.5 billion worth of tech and 8 years of work. And again, I think that's very heartening from an IT perspective, because we suck at knowledge transfer. We keep going, oh yeah, we'll put it on the wiki, this will never happen again. It will happen again. And that's okay, but the thing is, you need to realize it's going to happen again. I think a lot of us have got this optimistic mindset that everything's going to be okay, we're going to have the best case scenario. You shouldn't. Ideally, what we'd like to do is build systems that assume you're going to make mistakes. Assume that we're all going to do the dumbest thing and then it'll be okay. Now, if we were taking this pure NASA style, that would mean we build fallbacks and redundancies on those redundancies, and it would be the most infallible tank-like system that has ever been built. But are your business going to allow you to do that? No. They're going to want the new shiny thing. And that's okay. We aren't NASA. And in fact, I'm going to go and say we should do the complete opposite. By all means, do this, but that's not via wonderful resiliencies and things like that, other than in instances. So we've all been guilty of throwing that system into production that only supports the happy path. There's deadlines, and you can't get resilience, and you can't get monitoring, but the business is like, I want it now. So you put it in, you keep your fingers crossed. And normally, because we're lucky, we get away with it to start off with. But what you need to do is build systems that bring up more instances to take its place if you can fail fast and then recover fast. We are different from NASA, and that's okay. They have one instance released every 8 years, and if they mess up, it costs billions and billions of dollars. We can have thousands of instances these days. We can release multiple times a day, and I don't know what your job is, but it hopefully won't cost you billions of dollars if you mess up. And so that's okay. We can't build ultimate fault tolerance due to the amount of time the business gives us. Don't allow your processes to limp along. If there's a problem, kill it, start a new one. This is what Netflix have got very, very good at now with all the Chaos Monkey stuff, is they can kill off clusters and stuff will sprout up in its place. That's how we should be approaching our system builds. It's not like NASA where they can build redundancy and fault tolerance into one instance. Just have multiple instances that fail fast and bring up new ones. It's a much easier way of building systems. Just try and make it so that it doesn't affect the end user, but that comes down to your architecture. So yeah, and the other thing for me, as we were talking before about ingraining the idea of automation in from start, ingrain that idea of resilience in from the start, because as we just said, the business are never going to give you the time to go back and fix the resiliency. When you get the first node in, have that ability to something in there so that when it dies, something else comes up in its place, because you'll never get a chance to add it in as much as you'd like to afterwards. Build assuming that there's a dumb guy sitting in the data center that's going to kick out a cable at some point, because that guy does exist. And he probably exists in NASA as well. And that brings me nicely onto this topic of normalization of deviance. So let's talk more about that system. So we've thrown the system in on the happy path. It has no resilience, no monitoring in it whatsoever. And it's okay, it plows on and it does the thing, and the business is like, yeah, this is great. And you go, can I go back and fix it now? And they go, no, I want the shiny thing. And so you do the shiny thing, and it's okay for a couple of weeks. Then it hits a production issue and something goes wrong. And you go, okay, you scramble, you figure out what's wrong, and you go to the business and go, here's what presented, here's why it broke, we can fix it in 2 weeks to a month, is that okay? And they go, well, we know what it is now, and we can work around it, so don't worry about it, keep going with the shiny thing. And this repeats, so then a couple of weeks later, the bug happens again, it's not as much of an impact because you knew it was coming and you can work around it, and this repeats, and this repeats, and this repeats. And this has got a wonderful name, which is the normalization of deviance. You've accepted that there's a flaw in your system, and that's now just part of your system. Well, then what happens inevitably is boom. It really breaks. Senior management in there and the senior business, and they go, okay, so how was this allowed to happen? What did you do? And we go, well, we told you about this. And they go, no, it's your fault. You should have fixed this. You're the developers. You should not have allowed this to happen. And this happens fairly repeatedly, I think. It's a common pattern amongst developers. But it's not a developer pattern. That's the nice thing from what I've learned from doing this talk, is that this happens in all industries. This concept of the normalization of deviance was actually the term was coined with related to NASA. specifically the space shuttle incidents, the space shuttle crashes. Now, you'd kind of think space travel is dangerous. You know, you've got 300 tons of fuel making a bomb, 6 million parts made by the lowest bidder, 5,000 different technicians. It could possibly go wrong. You can understand that. But that disaster was completely and fully preventable. Because on the second flight back, the booster rockets, the white things next to the big orange one, they can't build those in one thing because they're huge. So they build them in small things and then put them together with O-rings. And there was damage found on that O-ring. And it came back and the contractors went, oh, that's not good. And you know, a bit of a panic because NASA were under huge pressure at this time to deliver, make money, you know, similar to how all our stakeholders are. And so the contractor went away and tested them under extreme conditions and came back and said, oh, you know what, we can deal with it under extreme conditions, they've not disintegrated, everything's going to be okay. And so it kept happening. So between STS-41B, which was 7 flights after this, the STS-2, sorry, and this flight, of the 16 flights, 13 of them came back with damaged O-rings. 13, it's a huge amount. But it had become ingrained in the system. They'd accepted, they kept going up and they kept coming down, so it's not a problem, it will be okay. It's the normalization of deviance. Now, the day that it actually flew, English is hard, it was a very, very, very cold day, colder than ever been flown before. And the contractor said to them, we don't want to fly this, we've never tried under these extreme conditions. And there was a very toxic relationship between NASA's business and the contractor. And they were like, what do you want me to do? Wait till the summer to fly my spacecraft? I can't do that. And eventually put enough pressure on that they allowed it to fly. And we all know what happens. But we've all had that conversation with our business where we said, you know, we can get it ready in time, but we're not comfortable doing that. And then it all depends on the toxicity of your relationship with your business, which is hopefully good, whether they will listen to you or not, which I'll go into that in a little bit. But the real thing to take from this, though, is when you've had that problem before where things have really exploded and you've had that big powwow, what I imagine you've said in your meetings then is, you know what, we're going to do better this time. We're going to write documentation. We're going to have support processes. This is never going to happen again, this sort of incident. We're all over it. And then it happens again. And that's a fundamental human thing because it is exactly what happened with Columbia. Disintegrated on the way in. That was happening from the very first space shuttle flight, STS-1. Between STS-1 and Columbia, 64 missions had that damage onto it. But even though they grounded the shuttle flight, even though they put all these safety measures in, this had already been ingrained as a normalization of deviance. They already just accepted that this was something that was done, and it was okay because the space shuttle went up and the space shuttle came down, and it was okay until this happened. Now, people don't learn. Hopefully your job won't result in the cost of lives or billions of dollars if you mess up. You know, I really hope it doesn't. But as a developer now, you know, this applies to us massively. And you have an advantage now because you have a name for this term. You know the term normalization of deviance. For me, it was just a nagging feeling of like Groundhog Day every time this happened. Surely we can do this better, but I could never put it into words and articulate it, which you now can. You have the normalization of deviance. We can take on more risk as developers than NASA can because of, you know, we have less damage if it goes wrong. But that doesn't mean we shouldn't be trying to minimize these deviancies because they do result in production issues, which then result in us getting shouted at and the business losing money. And it's a hard discussion to have because, as I said, the contractors on the day, they tried to persuade them not to fly for the previous shuttle, but they couldn't do it. And how are we meant to do it when it's like, well, you might lose, you know, a few £1,000s or dollars or whatever? What we have really, really important takeaway for me. If you find these things coming up over and over again, you should be recording them. You should have a deviance registry where you're saying, okay, we have this bug that we know is in the system and it's not going anywhere, but the business has said, we want you to plow on, keep going, keep going. If you're finding that your registry is getting really long, that is a symptom that your relationship with your stakeholders, your business, is broken. Because they should be trusting you. You are software professionals. We are not a service industry. We're certainly not anymore. You know, we provide value, and we should be trusted to know what our job is. So if you want to pull a stop-the-line mentality, if something goes wrong and you go, look, We need to stop this now because it will result in something going wrong in a big way and it's going to cost you a ton of cash or it's going to cause a multi-day outage or whatever. Your business should be trusting you to do that. If they're not, and if you're repeatedly finding they're not, you have a toxic relationship with your stakeholders, which you need to fix. And it's exactly what happened at NASA. NASA, in the reports, both the shuttle disasters had pretty much the same thing coming back constantly about there was a toxic relationship between NASA and the contractors, which is what allowed this sort of thing to happen. I'm not quite sure how to fix that relationship, though. That's coming in the next talk. Concept from Chris Hadfield, who's the Canadian astronaut who did Space Oddity on the space station and has then been just living off that money ever since, I think. Space is dangerous. It's a fundamentally dangerous thing. If you take this, right? This is the Apollo rockets. All of 5 miles a second to get you orbiting the Earth. Because when you orbit the Earth, you're basically falling around it constantly. And to get the fuel to get you that fast, you need more fuel to take the fuel up to get you to go that fast. And a lot of fuel. And then you've got the fact that you're doing cutting-edge science. The guys that went to the moon, this had never been done before. The amount of probes we lost when we tried to get them to the moon, I would have been petrified as an astronaut that I was never coming home. And then when you're in space, it's a vacuum. It's prohibitive to life, and there's micrometeorites, and there's radiation. And then you've got the maths involved to get you these places. If those guys carry a number wrong, again, you're getting lost in space somewhere. And apparently it took us to get to the moon 100,000 people. I can't get 2 teams of 3 people to work together, in a harmonized way. It took 100,000 people. I would be petrified of letting me sit on something like that. But anyway, so it's a dangerous game. But there's nothing as an astronaut you can do about that. You just have to hope everyone does their job. So what can you do if you are an astronaut to kind of make it better? Well, it turns out you practice a lot. I thought that when you came back from space, you kind of 'really hard. If they aren't on a mission, then they are rotating through all the roles. So it's the equivalent for us if we would become support for a couple of months, and then we would become business for a couple of months. They do all this thing. So Chris Hadfield was the capsule commander. He went and was the liaison to Russia. He was the robotics guy. You go through all these roles. So then you've got more sympathy. So when you're up there, you know what the people on the ground have done for those roles. And as someone on the ground, you know what someone up there has done. And it makes everyone work together as a much better team. But if you actually have a mission assigned, you really, really, really practice. To microgravity that we've got here. They have a full-sized International Space Station in a swimming pool, which I think is incredibly cool. But if there's an extravehicular activity like this, an EVA, I thought they kind of popped through the hatch, admired how beautiful the world was, twisted some nuts and whatever. And it turns out they practice for 6 months to a year for that. 6 months to a year of this hard work. And those spacesuits are not easy to use. And so they have a rule book an instruction book of what they're going to do during these EVAs. So they do the EVA, and then they go, okay, we could improve it this way and that way. They keep doing this, and then once they've got the happy path done, they do them again, and they throw spanners in the works. And they are asking, what is the next thing that could kill me? There's a guy whose role is, or a girl, sorry, a person whose role on these missions to come up with scenarios to just mess these people up. Their job is to come up with doomsday scenarios to scare them and to make sure that they've covered all the possible opportunities of what could go wrong. And then you run them, and then you document them. This is why you need 5,000 pounds of fuel to send it up, because there's so many scenarios that are documented. And it's a really, really good way of doing it. It's how you prepare for it. It's not necessarily about getting all the right answers. It's about making sure that you're prepared for whatever comes at you. First disaster in space where an oxygen tank exploded. Before this mission, the astronauts had said to the guy that comes up with the scenarios, and I quote, "These things aren't going to happen, let's stick to realistic scenarios." And so they had been, instead of doing hard scenarios, had been doing like easy, kind of nice wins to make you feel really good about it. And then on the way to there, the fuel tank exploded because the fuel tank, the cables inside it for heating away had been left on because the temperature gauge had broken, which then caused some batteries to do, and so on and so forth. And everything went wrong at once because you all work in IT and you know everything goes wrong at once. It's never like, oh yeah, this file's arrived late. Oh, this file's arrived late and the data's wrong and this service is down. And it's never just one thing at all. It's always these impossible scenarios. Now, you can safely say that after this, they were allowed to create whatever crazy scenarios they wanted. And that was a good thing because they already knew that this stuff paid off in spades. If you take, oh, sorry, let me just do this. It's brilliant. These simulation ideas, they work. But what I was going to say then was they'd already been proven to work before this, and that's why it baffles me that they stopped. Because on Apollo 11, so when we actually landed on the moon for the first time, the night before they took off, the backup crew were running scenarios. And the guy that comes up with them threw a 1201 error at them. And they were like, I have no idea what this is. So they phoned back to Mission Command and were like, what do we do? And Mission Control was like, we have no idea about this either. Abort, abort, abort. And then afterwards they got and they had their powwow to say, okay, well, what should we have done? And the answer was they should have kept going because it was a computer overflow error. And the computer would catch up, it's just that it was really busy at the time. 5 days later, when Armstrong was heading down to the moon, this didn't come up once. 1201 was on repeat like every few seconds because the computers were so overloaded because they'd messed some stuff up to do with the radars. And the history would be very, very different if these scenarios hadn't been run. They would have had to abort. So these scenarios work. But how do we apply that to us? So as I said, they spend 6 months practicing this. Are you going to get 6 months with your users to run them through scenarios? I can't even get 60 minutes with my support team to tell them how to deal with stuff. So the answer for me is that we as developers can practice a lot. We should be practicing failure scenarios so that we get good at it. But the thing is, I imagine you guys already do. I don't know about you. I have this thing called a disaster recovery drill. And once a year, in a very well-understood fashion, at a very well-agreed time, with all the other teams, we fail certain parts, we know it's coming, and we prepare our systems, and then it fails, and then it works correctly as we expected because we had 6 months to prepare for it. We give ourselves a pat on the back, and we go, yes, our system can deal with recovery. That's not practice. That's utterly, utterly pointless. There's a good quote from Armstrong, again, from his stays in the simulator. They tried to operate perfectly all the time and avoid the problems. I did. Your system and having different failure scenarios would reveal useful information about different parts of the system and how it behaved. That's how you learn things, not by getting greens and patting yourself on the back. You want stuff to crash in dramatic ways so that you can then know, in a safe manner, obviously, in a test environment. And so then you can go, okay, we know what happens when this happens, so we can deal with it if it gets thrown at us in production. And we need a software equivalent. Obviously, we've got Chaos Monkey, and Chaos Monkey is brilliant. And all the Simian family where you can take out nodes or clusters, and that's great, and that's getting you comfortable with failure, which is what this is all about. But I still think that there is a missing key point here, which is we have no way of failing the actual intricate details of your application, of the application software behavior. And I can't tell you how to do that because it's specific to your application. For me, we have to all be writing these application harnesses so that I can input errors into my system and have it cause havoc. For both the Space Shuttle and the Apollo missions, they had this. They had a test environment where a guy could sit behind and go, here's lots of 3 errors at once, and see how people deal with it. And you need that for your systems. You need to be able to wrap it in some sort of harness where you can go and input errors and cause people to try and figure out how on earth to fix it so that you can become practiced and better at it. And there's some ideas, bad data, queue failing, upstream, downstream. And then you have to make sure that you can put in all of those problems at the same time. Because as we discussed before, you've got to expect cruddy data arriving out of order at the same time your backup server's down. And if you can practice that, and if you can throw your team into that, and they can come out of it and fix it and know what's going on, you've won the game there. So for me, the way this looks like is that you get one person from your team who is going to be the chief nasty person, watch my language. And their job is on one day of the week to come up with this crazy error, and you have to go and fix it. And I can guarantee the first problem you'll find is that your monitoring isn't in place, and you will have no idea that it's an error, because most developers only discover there's a problem when the business phone up and say, there's a problem. And that shouldn't be. You should know that. You should know that there's an issue. So get your monitoring in place, and then run the scenario again. And keep doing this. I'd recommend once every 2 weeks, once every month. And if you're going, I can't spare my whole team for that amount of time, you shouldn't. If your whole team, if there's a problem in your system and your entire team is downing tools and running at it, you're not handling these things correctly. You should only have, unless it's a stop the world failure, you should only have 1 or 2 people dealing with this at any time. Practice dealing with the failures, because when you keep doing this, you'll get really good that when something goes wrong in production, you'll know what to do. You will know who to notify. You will know exactly what emergency procedures you need to go in. Oh, I need to ramp up another cluster or whatever. You only get good at this stuff with practicing. It's why the simian army works, and that's why this idea of testing your application failing also works. Becoming really good at dealing with stuff going wrong. How did the team respond? Did they respond correctly? Did you realize there was a problem? If you've got this stuff down, then your team is really, really good at support, and you're not going to have that many issues. If something goes wrong in production, it's just clear sailing. It's not a problem, because you'll have put the tools in place so that it's not so much of a problem for you. And then obviously, did you fix the problem? It would be nice if you fixed the problem. And even with all of this, because one of the nice things is, when you've run all these scenarios, is you can hopefully build yourself up some sort of documentation to say, okay, here's, if these things happen in the system, here's how we deal with them. But you're still going to miss things. And that's okay. Even though you can get really... you're going to be really excellent at dealing with it. There's just one final quote I'd like to leave you with, which is from the Curiosity. Are throwing absolutely every problem at the system that they could to see how the team could deal with it. That's hugely important. Do you think your team is psychologically steeled to be able to deal with any production thing that goes wrong? I'm guessing not. Practice really does make perfect. And slightly ahead of time, that is everything finished. There was so much information from this that I've left out of here to do with testing environments, using the vomit comment and stuff. Really good stories that I am trying to put it into a small ebook. So that's available for pre-order. It's on LeanPub now, so as soon as I start writing it, you get content. So if you want to read that or you just want to buy me a coffee, cgiq.co/astro. It also has all of the bibliography of everything that I've read in preparation for this. So if you want more space books that I recommend, they're all up on there as well. Thanks very much.